Hey everyone, welcome to another Haskell study group. I'm your host, Ron Batum with Atlanta Functional Programming. My apologies to folks who have been waiting on. We had a couple of technical difficulties earlier and we had to resolve them. So we're back on though. Today's going to be a fairly short discussion because we are continuing our discussion on how to build Haskell projects using Stack. Last time we discussed this, just as a review, we created the simple project using Stack New. As many of you know, Stack is a curated package manager for Haskell that essentially creates a package and as well as maintaining dependencies for you in such a way that you don't have to necessarily go out and understand Cabal, the common application build system for Haskell. Uh, the difference mainly being that Stack allows you to build multiple dependencies using with Cabal files, whereas with Cabal, usually you are actually working with a single module and creating up a build system for that. So you can deal with multiple modules, multiple libraries when you're using Stack. Stack itself was designed with the idea that eventually people will like to be able to um, leverage Haskell as a real programming language, for lack of a better term, to write real industrial private sector based projects, and a lot of projects end up using Stack as well. So once you learn Stack and understand how it works, obviously that's going to really help, move on your journey, so to speak. So that way, you don't have to necessarily um, reach out and use another package manager, or you hack even writing your own shell scripts to actually set up your build system because Stack does it for you. Um, Last time we kind of went through the majority of um, uh, what a package is. We created this library here, and recall that when you're building a library you're building essentially what's called a module in Haskell. Top level declaration is going to be at the top. The name of the module is obviously going to be the same as the name of the file usually. Um, if you go and change it to something else, I think it complains if I remember correctly. After the name of the Haskell module, recall that we have in between the parentheses the list of exported symbols. That is a list of functions that you want to export it out of this module so that other folks can actually use it when they import it into their own libraries. And we've defined a couple of functions here that returns the IO monad that leverages uh, just printing a string out. And we actually used this when we created, obviously, our main application where we actually imported the library and we just called the function here. Nothing major here. Of course, there's more to this importing modules than what we covered last time, and I thought we'll continue covering some of that today, as well as making our program do more than just printing strings out to the console. It will make it a little bit more interactive, and in the process, we'll understand and we'll start digging into the concept of the do syntax, as well as um, introduce a little bit more about the IO monad without getting into monads in general. Um, Finally, um, I'm not going to cover the Hangman game that's provided in the book. I think folks who have the book, I encourage you to actually write out the Hangman game step by step using the examples that are in the book, actually go through it because you'll understand a little bit more about how project structure is created. It will allow you to reiterate some of the stuff that we talked about in the last episode on how to set up your Stack project, download your latest version of the Haskell REPL, as well as be able to um, understand how to set up modules and write your modules and create up, a very nice ending application. This way, at the end of it, you'll be able to actually start up and write your own projects using some of the steps that are provided in this chapter. Obviously, something that's missing in this chapter that I know most of you real world programmers out there and engineers out there are probably thinking about that we haven't covered yet is the topic of testing your software using unit testing frameworks. And we will cover that next week, and that is the next chapter in our discussion. So, folks who are trying to, get ahead of themselves, and you're interested in, how can we actually test our software? I encourage you to go ahead and read the next chapter, chapter 14 on testing, which will cover actually quick check and actually, which is a common technique of using rules-based testing, uh, and we'll get more into that when we talk about testing next week. The final topic that we're going to be covering tonight is very quickly is adding a new type inside of our modules and exporting new types using uh, uh, what's it without getting into some of the examples that they are talking about in the actual Haskell book on the Hangman game. Okay, so let's get started very quickly here. Um, we've introduced before, I think, in some cases, and if not, this is going to be the first time that I may dig into this, but um, this notion that your main function, your main entry point, and recall that main has to be available for your application to actually be built. So when we use, say, let me see if I can actually pull up a shell here, e shell. Actually, hold on, let me do this to start up our Haskell REPL. And let me split my window here and open up an e shell to give what I was going to talk about. Remember when we actually started up our project and building our project, we actually required our executable to have a main entry point, okay? If you do not have a main function here, okay, this just like any other language that needs a main function, if you just simply comment this guy out here, recall that it's going to complain that there is no, obviously some entry points here. And additionally, if you name this something else, and this is more to the point, let's say we call this foo, this is going to also um, cause some issues too as well, because again, it's not the main entry points. It's thinking that it's a function called foo, all right? And this gets complained, and you'll end up getting this error. Main it can is a function just like any other function, and it allows you to be able to call expressions like we did here. You can see that this function specifically, main is nothing more than an alias to an existing function that's already available in our lib library, as we saw earlier. Um, if we open up lib here, all right. But main can actually do much more than that. Any other function actually can do much more than that. Um, if you wanted to do more than one thing, usually most people want to, run things in sequence, right? There, yes, yeah, okay. Give me just 1 second here. Um, my- okay, can you see it now? Okay. You need to be able to actually run things in sequence, and this becomes important when we start talking about, you know, this notion of what we were talking of. creating an interactive version of a program. Let's say that we want to just simply ask somebody their name and then, you know, call a module. Let's call this here. One second. Let's first build out a function here. Let's say that in our lib, we create a function called say hello that returns an IO monad, and say hello, and let's say that it takes an X and it returns a message, okay, and returns an IO monad. And if we do say hello X, it will just do put string line uh, hello, and we will, and let me be more explicit here. It's actually, we need to provide a proper type signature here, and we just say hello X. Okay, so now we have this function. Obviously, this is a top level binding that is actually unused. So let's go ahead and make sure that we, export it. Say hello. So now this is an exported function. And let's say we want to actually use this. Well, this is a function right now that will just, take in any sort of thing. So this isn't going to be doing much, but if we go in and, try and build this, obviously this will compile our code. And what is it complaining about? Oh, my apologies. I think I have to return. Yes, my apologies. I tried to concatenate the wrong thing. Okay, this now works. Okay, I should have paid attention to that type error there. Just remember, sometimes a good set of parentheses will take the precedence. What is happening earlier is putStringLine was taking hello and trying to concatenate an IO monad, which is what putStringLine is returning with X, because plus plus is infix, but I think putStringLine was has higher precedence, so it's not going to actually just automatically concatenate to two things here. So if we try running this, obviously this is going to give us, our app that we run. So we do stack run, I think is called what we use to actually build it. You can see that our hello world program actually does what it expects. But this is pretty useless because we want to be able to actually get some input from the command line. So the first thing we need to do is be able to run things in sequence a little bit and actually get something from the command line and actually, display some sort of prompt and, make things, interactive, right? So to do that, you need to first talk about the do syntax. Do is um, a function, and it's a notation, really, a keyword that allows you to write things, in a little bit more conventional way in sequence. Uh, it's really a syntactic sugar that allows you to run things in sequence, and apparently um, it's not really necessary, but to make what we're talking about do something without the do syntax, you have to introduce the concept of monads, and we're not going to touch base on that right now. When we talk about monads, at some point we could revisit. I'm thinking that we should revisit this, and obviously, see how we could do it without the do syntax and show the differences. But until we cover that topic, for now, just know that what this is doing is it's creating uh, a monad that allows you to sequence monadic actions. Okay. Um, so obviously that includes expressions, but it also includes function calls. Okay. So let's use this syntax first, and then cover what how to leverage it in other contexts. Okay, so the first thing to do is we need to import something here because we're going to end up leveraging some uh, buffering features that aren't currently available by default unless we actually import this library. If you want no buffering, so it's more interactive, you need to import system.io, which includes something called hset buffering, which allows you to talk about the horizontal buffering inside of the console. And we're just basically configuring standard out to don't buffer, just throw stuff straight directly into the console as soon as you get it. Now let's create a prompt here that will allow us to, ask what a person's name. So like, what is, sorry, put string line. No, put stir is probably better. What is your name? Okay. So now that we have, um, our prompt, we can go ahead and now grab something from standard in. To do this, we need to assign it, a binding. This is a local variable within the context of the do notation. Outside of the do notation, it will not exist. And it's think of it like a scoped variable, a local variable that you have inside of a function. And to get something from standard in, we have this function called getLine that essentially waits for a new line character when you hit the return key, especially on the keyboard, and it will actually go in and then take whatever text you grabbed from the before the carriage return new line. It will then bind it to name. Now we have a string coming from that. We can actually call say hello on names, and we can just go ahead and then print it out, and then we're done. Okay. So this is a pretty basic function or standard function when you're first getting used to learning, you know, any new programming language. But it shows a lot of stuff here, right? Mainly, we can configure how we interact with the console. We're showing things running in sequence. We are actually doing getLine and so forth. And more importantly, we not only have the ability to run this on the shell after building the executable like we did this. If we actually load this into our REPL here, just do main, you could see that we can actually interact with it here. Okay, which is pretty neat too as well. So you can actually test your main entry points as well from the console. But of course, let's make sure that the same thing happens here. Obviously, let's call it Jack, and if we hit it, we can actually see that, we can actually uh, get stuff from the standard input and actually run it. Okay. A couple things to note that you may have noticed very quickly that I'm just going to reiterate here. Main always must return um, a IO monad. Uh, the reason is because of the fact that it's going to be dealing with a lot of syntax coming in from standard in and other places. It's very rare. I don't believe you can actually change this. If we do anything that does that uses do, it automatically means that you're going to be using IO. I don't know if you can use do in other cases. I'm still kind of learning how some of the syntactic ways to do it, but my current understanding is do uh, um, essentially returns IO. To do syntax specifically, like I said earlier, allows us to do sequencing, as you can see here. Each of the sequencing are considered a monadic action, which is nothing more than it takes in a monad and returns a monad. Okay. After that, obviously, it whatever you're doing within the actual functions that may return a monad, that could be any sort of things. It could be all the function evaluations that we've talked about before already, and anything that's in the standard library. But at the end of the day, when you're dealing with monads, um, it your function transformation pipeline, and IO is one common example. It's going to probably be one of the monads that you're going to be using a lot. It creates these monadic transformation pipelines where you take in a monad and return a monad. Again, I know some of this is going to be over a lot of folks' heads who are watching this right now, but bear with it. When you don't, the main point is you don't necessarily need to know what a monad is at a deep level before you start using it. Okay. And the do syntax is one of those cases where you don't necessarily need to know how the underlying monadic machinery works. You just need to know that when you're using do, your function is going to be um, a monadic transformation, essentially. It's going to return a monad at the end. Okay. Uh, the one thing to note is, as you saw earlier, um, is getLine being a monadic transformation, a monadic action. It allows you to uh, take what's in the monad and it behind the scenes, um, it will bind that value that the IO monad returns. So getLine more specifically doesn't return a unit, has what this is called here. When you see open parens, close parens, that's returning kind of a unit type. What getLine returns is an IO monad of types with a string value. But this assigning notation that you see here, it unwraps the value and binds the value that's returned by getLine to the variable name, okay, which in essence will then create like an IO unit at the end because since getLine itself is an IO string, and we're binding the string into the name, the next value is going to be an IO unit. Um, in the case here, um, we have a final binding action that returns an IO unit in the case of say hello, because hello calls put string line, and string line essentially returns an IO unit. But we could certainly do something interesting instead. We can actually create a function. Let's say uh, create a different let's go ahead and create a function, okay, called uh, get user input. Okay, what this does is it will return an IO and it will return a string. Okay, and what get user input does is it will grab the name, okay, and let's put this put a couple things here, name here, and put occupation. Okay, so we're just going to expand this input interactive program to include two things. All right, and what we're going to do is we're going to actually return a monad. Okay, and this monad is actually taking the two values that we provided, and we're just going to, create a concatenation of these two. Obviously we can also, at some point create a structure of this. You could think of this like if you're doing data entry, at some point you may want to create a structure for this, or a record type, and actually record some of this information and then have some convenience functions on that. I'm not going to talk about some of the design discussions here. For the sake of simplicity, we're just going to simply return kind of the string representation of this information. Okay. To return this information in such a way that it can be used by put string line, and others, we could simply just do a return here. Return itself is a function that takes in a monad and takes in a value and returns a monad. All right. You could think of this as a constructor of monads, all right, depending upon the monad that you're trying to construct. And here we're just going to go ahead and take in the value name. We're going to just concatenate this really simple thing here. Age. All right. Sorry, not age. Occupation. Okay. And now, instead of doing this, let's say that we say, please provide the following information. Okay. And we'll just say info equals get user input, and we'll just say put string line info. Okay. This is going to do kind of the same thing that we did earlier. Oops. Apologies. I just accidentally deleted that. Okay. Whereas we now have multiple information. The difference is that whereas before this function was just simply taking an input and returning it, we're now actually creating a return value of this function, but we returned it in such a way that it's wrapped in this object, all right, called a monad. Okay, that's the IO monad. Okay, and it is then bound when it's assigned to info, because of the syntax here actually essentially does what's called an unbind. It actually unwraps the value from the monad and returns it and puts it into the info value. Okay. Again, when we talk about monads in more detail, and I know I'm beating a dead horse here, this will become clear. The syntax why return is used will become clear as to what it's doing and how it actually fits into the entire machinery that is monads in Haskell. So now let's just quickly, provide a quick thing here. So, let me put name, occupation, regular guy, or something like that. Why is this? I think Emacs is locked up right now. Let me see if I could open up another thing here. Let me see if I can kill all Emacs. Okay, my apologies. We'll get back into our regular scheduled program in just a minute. Technical difficulties always ends up happening, but it's the name of the game. Okay, so let's see if this shows up. No, it's not. Okay. Let's do this software Haskell hello main main no source hello setup oh app main.hs. There we go. Okay, start this up again. Give it a second. Okay, and let's do this. Okay, so now when we run it, we could do John Doe. Give it a second here while it's grabbing information from. It's going to pause a minute here. This is really, really odd. Let me see if I can get this a little bit to show you how this is working in the normal REPL. It might be that it's just locking up with standard in by because of other computational processes that are running on my machine. So let's do this hello. Okay, and do a stack run. Well, let's first kill Emacs because this is going to be doesn't really matter. Okay, and kill even GHC, any GHC stuff that's happening. And let's go ahead and just fire up Emacs and set up our environment here pretty quickly. While this is just setting up, let's go ahead and run stack run. And I can just show you this program here pretty quickly. Here, when you do pretty interesting piece of a feature that I forgot to mention about Stack is that if Stack recognizes if there are changes in your source code and if it hasn't been updated yet, if the executable hasn't been updated yet, it will automatically recompile everything. So if you just do a simple stack run to test your program, you'll get an updated executable almost immediately. So here you could see, let me just clear this up so you can actually see this here. You can see that immediately, um, occupation, regular guy. You can see that immediately once the standard in is in, that we actually can print this out and we'll actually get what we want. The main thing to take away from this is two things. One, do syntax allows you to sequence actions one after the other. Two, your main program that ends up creating those sequence actions, those monadic actions, will return an IO monad of some sort. Again, don't worry about what a monad is right now. And three, if you want to create other functions that interact with standard in and return something that can be used in uh, put strings, instead of actually returning a value like you would normally do, returning of an expression, the computation, in do, because you're dealing with, and this is only when when you're in a do block. Okay, let me just warn you on this. This return is being used because you are in a do block when you are defining your functions. Okay, in other cases, normally, as you know already, we've actually dealt with this in other examples in Haskell in previous episodes. A function simply can returns values. All right, it will take in a value and return a value. All right, but because do requires that value to be wrapped in some sort of monad, it's using return to lift the bindings that you created from standard in and stick them in a monad that can then be used in later transformations. All right. So if you bind that IO with the string, you end up getting, what we saw earlier. All right. I hope this makes sense. This will become extremely clear when we visit and understand functors, applicatives, and monads and other things. But for now, just remember these rules. If you use do in another function, you are going to be returning an IO monad of some sort, and you're going to have to return whatever values to lift those values into the monad and construct a monad before it can be used in other do pipelines. Okay, I'm going to pause here because I'm sure there's going to be questions. Folks who are watching on the live stream, feel free to post um, the questions, um, and and I that's a good point. You might be right. I don't. I haven't thought about that. That's actually a good point. This is why yeah. Well, I mentioned IO because well, for one thing, chapter 13, all the examples, the first thing they say that uses do. The first thing they say is do introduces the block of IO actions. They don't specifically say that do can be used in other cases. But, again, I, I like you, I am speculating as to it might be able to do more because really it's a sequence monad, right? It's right, right. Wait. Repeat the monoid part. Why do you think do is a monoid? Yeah, wait. You say sorry. Why do you say what did you mean by a monad? Okay, so a monad is a monoid. I know it's a monoid because in category of endofunctors, right? It's a monoid because it's an associative operation that you can that you apply to two values and you can what is it? Right. It's mapping it back into the same category. Exactly. Right. Right. Do does nothing more than sequencing. sequence stuff. It just says, hey, until the end of this block, this do block, all right, the order in which you see the expressions is the order in which I expect them to be executed. Um, right, right, right. And if you look at the type signature of return, because you brought it up, for folks who are following along in this discussion, this is very important. Return does not specify any monad. All right. The top level thing that it's saying is the input m that it returns must adhere to the monad type class. Okay. And we've talked about type classes. What this means is if you're defining a monad, what you're really doing in Haskell is you're creating an instance of the monad type class to go and define your monad. And you can go and look into the monad type classes. We'll talk a little bit more about that when we touch on and discuss the monad type class in detail. But when you're reading this signature, please recognize that because that's telling you that return can construct any monad. All right, return is what you're going to be using a lot when you are constructing monads. In fact, because that's what actually allows you to lift values into the monadic world to deal with your transformations. Sorry I just want to clarify this one particular piece for folks who are watching the stream. Hmm. Hmm. Right. So here's what I'm thinking, right? I mean, there's multiple ways of implementing this, but I would think that without do, doing, one way of performing, because I really don't want to keep saying do, we keep saying do a lot. Instead of using the do syntax to sequence operations, one way of performing the same set of operations in sequence is creating essentially a monadic transformation composed of things using the state monad, right? Because because a state monad, I think, allows you to say you're moving to the next state, right? And you could determine how to set that set that up. I do. So I would think that that's probably one way of actually. In fact, I'm pretty sure. I'm almost certain that. Right. The difficulty of this is this here actually, to be quite honest. I don't know how to essentially what functions to call that ultimately implements this piece without doing this syntax. Return get line. Actually, you can't actually. Right. Right. It's creating an IO string, but the unwrap is happening in the left in this operator. So and unfortunately, yeah, I have to think about this. This is a very interesting challenge. Let me think about how might I implement this because I really don't know about this particular piece. I mean, I see what you're saying because it would be pretty straightforward to essentially do what we do in other languages, where you could just simply call a function and return, um, take the return value and automatically use it as an input for the next value. But in this case, unfortunately, we're not actually using the return value. Well, we are taking the return value, and in this notation here, we are grabbing we're calling another function. So this return value is actually passed to another function that ultimately returns a string that gets bound to the thing. So that second piece there is something that I'm missing, and I have to think about what is the sequences to actually pull it all out and put it together, because then ultimately that will actually do that, and that would yeah. Okay, I see what you. I'm gonna make a note of that for folks who are watching, uh, and see if because the challenge has been thrown, let's see if I can actually come up with it, or am I going to fall flat on my face? Um, yes, a monad is a monoid. First, you're if we can prove that, then the next couple things it becomes pretty straightforward, right? Yeah, right. 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 So, uh, one thing to note for folks who have seen these two examples of do notation, especially with return, is return can take any type. All right. If we go back to the return function signature, A is just a generic type variable. It's a parametric type function. All right. So you could pass in anything to it, and it will construct the appropriate monad that the function is expecting you to construct. So if you're saying, "Hey, I want you to return an IO bool," you could certainly do that. If you want to return an a IO of your object that you just constructed because you wanted to actually take the information that we provided and create a type construction of it, you could certainly do that. It it it's a the notion the beauty of this function and the beauty of the parametric types and generic types allows you to take your generic algorithms and generic functions and write them once, and then you don't have to necessarily do them all over again. One thing that's pretty interesting to take notice of, all right, and to be aware of for new Haskell programmers, all right, and I cannot stress this enough, is you might be looking at this and thinking to yourself, I can actually use do to actually just write all my functions in a sequence, right? Please do not do that. Um, Best practice dictates that you do not you overuse do blocks. Okay, it's considered bad Haskell style. All right. Um, you want to actually, especially, and this is especially important, you do not want to write something stupid like, let's say we have a function foo that returns IO string, and then you do a foo equals do return blah. All right. This is bad, a bad function. Do not write a single expression in a do block. All right, this is just not. Why would you do this? All right, this is. I cannot stress this enough. Do not write it this way. All right, there are plenty of other ways of actually handling your expressions. Um, when we start talking about when we start talking about real world monad programming, we'll introduce something called the bind operator, and we'll use that operator. And just to give you a hint for folks, bind is basically this guy. We'll use this operator to actually deal with these kinds of single line expressions. All right, so you don't even have to necessarily use return. Return will automatically be engulfed in bind. All right, but until then, don't get into the habit of writing something like this. All right, this is just going to piss a lot of experienced Haskell programmers off, and they will look at you with the malice and wondering what are you doing? All right, did you actually learn this stuff? So just do not do it. All right, you might have the inclination to do it, but I'm going to stress again: do not do it. Right, just don't do it. Just don't write single line do blocks. All right, just throw it out of your memory. All right, just I pretend I didn't even show that example earlier. Right, I deleted it from the file. Yeah, I know it's going to be on YouTube. Yeah, you can rewind it and check it out, but just don't do it. All right, just do not do it. Okay. One of the main reasons is it affects composition of your functions, and you'll see this when we start using bind. Bind allows you to compose a lot quicker, but writing those do blocks like that, I don't believe. I mean, first again, it's bad practice because it's pretty useless. But additionally, I think I'm pretty sure I read somewhere that it affects how you compose your functions, because now you're forcing sequence happening instead of allowing, Haskell to do certain types of optimizations with your code once it knows that you can compose those functions. So one final repeat, just don't do it. Do not write single line do blocks. All right. Um, uh, what is the final thing that I want to talk about? Didn't know the function. You can put. Okay. So let me go to this one. Okay, we actually covered the majority of this stuff before in previous things. I thought we needed to introduce new type, but I think we covered new type last time. So, okay, so that is it for today this week. It was a short week. I kind of figured that it was going to be pretty short. Next week, we're going to be talking testing. Particularly, we're going to be introducing Quick Check for folks who are interested in checking it out. Quick check is only covered in a very superficial level in the chapter, just to show you how to get started with learning what quick check is. Um, I encourage you to go look at the quick check project, um, which is a way to write pattern-based testing. Um, it's specifically written to do a uh, yeah, it's specifically for doing uh, I would argue that they call it pattern-based testing, but really a better name for it, in my opinion, is it allows you to write like fuzzer types of tests where random inputs are actually put into your functions, and it will obey. It'll essentially just run as many different types of variations on those random inputs and see if any one of those fails based on some contract that you wrote for a given function. Um, what you start with is you build something called a functional specification, and it'll work from there. But again, I'm not going to go into too much detail about this. Folks who are looking into a quick check and want to have more of a detailed tutorial, I encourage you to look at the project website for it, as well as I think Wikipedia has a bunch of references to different bindings for QuickCheck. Well, different ways of implementing it. QuickCheck was actually implemented in a lot of different languages, so this is kind of like the first of them all. So we're going to be talking about that next week. Uh, Additionally, just a reminder, AFP is looking for speakers. Atlanta Functional Programming has been running its meetup online. If you are, regardless of where you are geographically, if you are interested in giving a talk on functional programming in any language, we are language agnostic. Feel free to ping me. I'm available on the Lisp channel on functionalprogramming.slack, and I do occasionally squat in the Lisp Discord server from time to time. So you can ping me on there too as well, and I will get back to you with your ideas. Um, Folks who are in the Atlanta area, I know you've been probably aching, wondering when we're going to be starting in-person meetups again. I do apologize due to these tumultuous times that we're living in. We are in the process of finding a venue again. I'm hoping to get that kind of resolved soon. But realistically, it's probably going to be after the new year, maybe even February, before we have something kind of concrete. Uh, in that time, we are still, running stuff online. Come join us, every week for a Common Lisp study group, a Haskell study group. We are trying to give talks too as well. If you guys are interested in giving talks as well, just go ahead and ping me at the representative places. If you're in our meetup page and a meetup subscriber and you want to also, give a talk topic or have suggestions, feel free to also message us on Meetup and we'll get back to you as well. So until next week,